What secrets vanish inside a black hole? Could the very core of the universe be hiding information from us? Are we on the verge of discovering that the impossible isn't so impossible after all? Stay with us as we unravel the mind-bending truth about black hole. And don't forget to subscribe and ring the bell, because what you're about to see will change the way you see reality. Number 1. A one-way street. Black holes are the ultimate cosmic traps, regions in space where gravity is so intense that nothing, not even light, can escape once it crosses a certain boundary called the event horizon. Imagine a place where the laws of physics, as we know them, twist into something almost unimaginable, where space and time themselves are pulled into a vortex of infinite compression. Anything that crosses this line of no return is effectively trapped forever. The center of a black hole, known as the singularity, is a point where density becomes infinite, and the familiar rules of physics break down entirely. Time stops, space ceases to behave normally, and all matter is compressed into a location smaller than a proton. This boundary defines the one-way nature of black holes. General relativity predicts it perfectly. No signal, no object, no information can escape once it crosses the horizon. But when quantum mechanics enters the picture, this one-way street becomes more complicated. Quantum mechanics suggests that even empty space is far from empty. It teems with fleeting particles that pop in and out of existence in pairs. Number 2. Something out of nothing. The idea that a black hole can give something back from nothing is one of the strangest and most fascinating results of quantum mechanics. Hawking radiation emerges because pairs of particles constantly form and annihilate in the vacuum near the event horizon. When one particle falls into the black hole and the other escapes, the black hole loses a tiny amount of its mass, shrinking over unimaginable periods of time. The escaping particle appears as radiation, a kind of energy emitted from the black hole, slowly draining it. This challenges our classical intuition because it seems as though the black hole is creating energy from empty space. But quantum physics allows for such processes because the vacuum is never truly empty. It is alive with temporary particle pairs that exist for infinitesimally brief moments. The particle that falls in carries negative energy, balancing the total energy budget of the black hole as it emits Hawking radiation. This subtle bookkeeping ensures that energy is conserved even as the black hole evaporates. From the outside, it seems like magic, a region of nothingness slowly radiating away energy. Yet the deeper mystery is not about energy alone, it is about information. Number 3. Einstein's enemy. Entanglement is a concept that makes black holes even stranger. Particles that form together can remain connected across any distance, influencing each other instantly, no matter how far apart they are. Einstein famously called this spooky action at a distance because it seemed to violate the idea that nothing can travel faster than light. Yet entanglement is real and well-tested. Measuring one particle immediately tells you something about its partner. In the case of a black hole, the particle that escapes as Hawking radiation is entangled with the one that falls in. This means the state of the outgoing particle is linked with a particle hidden behind the event horizon, creating an invisible connection between the inside and outside of the black hole. The challenge arises because this entanglement produces a form of quantum randomness. The radiation seems completely random if we observe it, making it impossible to reconstruct the information about the matter that entered the black hole. Number 4. Information lost. If black holes destroy information, as Hawking initially suggested, this would break one of the fundamental principles of physics, that information cannot be obliterated. To visualize this, imagine burning a book. The book is gone, but the smoke and ashes carry traces of the words. In principle, the story is not entirely lost. In contrast, if a black hole destroys information, there is no equivalent trace outside. Hawking radiation appears completely random, hiding everything that fell in. Scientists measure this randomness using a quantity called entanglement entropy, which quantifies how much information is unknown or scrambled. Early calculations suggested that as the black hole emits radiation, the entanglement entropy continues to grow, reaching a plateau implying information is permanently lost. This violates quantum mechanics and has been one of the most vexing problems in theoretical physics for decades. Number 5. The Firewall Paradox. Some proposed solutions to the information paradox suggest a dramatic scenario: a firewall at the event horizon. In this hypothesis, the entanglement between the inside and outside of the black hole is broken, creating a wall of high-energy particles that incinerates anything falling in. This would solve the information problem by preventing entanglement from continuing across the horizon. But it contradicts general relativity, which predicts that the horizon should feel nothing special to someone falling in. This paradox, known as the Firewall Paradox, highlights the extreme tension between quantum mechanics and general relativity. It suggests that our understanding of black holes requires radical new thinking, a willingness to consider that the fabric of space and time behaves in ways that defy common sense. Number 6. The page curve. One of the breakthroughs in resolving the information paradox involves the page curve, a graph that predicts how entanglement entropy should evolve over time if information is preserved. Initially, as a black hole emits radiation, entropy rises, reflecting growing randomness. At a critical point, called the page time, entropy reaches a maximum and then starts to decrease, indicating that information about the infalling matter begins to emerge in the Hawking radiation. This contrasts sharply with Hawking's original calculation, which showed entropy rising forever. Generating the page curve requires considering quantum effects on the black hole's spacetime itself, not just on the particles falling in and out. This insight has been pivotal, showing that information may not be lost but subtly encoded in the radiation through a mysterious connection between the interior and exterior. Number 7. Fluctuating wormholes. Quantum gravity introduces another twist. Wormholes, tiny tunnels connecting different regions of spacetime. When considering multiple copies of a black hole and its radiation, quantum calculations suggest that the interiors of black holes can swap through short-lived wormholes. These wormholes allow what is called the island inside a black hole to be non-locally mapped onto the outside, making part of the interior effectively visible to the external universe. This is counterintuitive. The inside of a black hole, once thought unreachable, can influence the outside through purely quantum processes. Such wormholes are rare and fleeting, but they offer a path to reconcile quantum mechanics with black hole physics, preserving information without violating relativity in an obvious way. Number 8. Islands beyond the horizon. The concept of islands helps clarify how information escapes a black hole. The island is a region inside the black hole that becomes part of the outside radiation due to these wormhole connections. When calculations include the islands, the entanglement entropy of the radiation matches the expected page curve, suggesting information is preserved. The island itself is large, extending almost to the event horizon, yet it behaves as if it is outside. This idea challenges our classical intuition about boundaries, showing that in quantum gravity, what is inside may also be outside, and the black hole's secrets are not entirely hidden. Number 9. Quantum entanglement and non-locality. All of this depends on a deep property of quantum mechanics: non-locality. Entanglement allows particles to remain connected over vast distances, and wormholes magnify this effect for black holes. Information does not need to physically traverse the event horizon. It can appear outside through a quantum mapping. Gravity, it seems, respects quantum mechanics in a subtle way, using the structure of spacetime itself to preserve information. Number 10. A universe of mystery. In the end, black holes are laboratories for the universe's deepest laws. They force us to confront the limits of our understanding, combining general relativity and quantum mechanics in ways that challenge intuition. With Hawking radiation, entanglement, firewalls, islands, wormholes, and the page curve, we are beginning to see a self-consistent picture where information is not destroyed, but preserved in a highly non-local fashion. The interior and exterior of a black hole are intricately linked, and the mysteries of these cosmic giants continue to inspire new ideas about space, time, and the nature of reality. Black holes remind us that the universe is stranger, more beautiful, and more surprising than we could ever imagine.